Good morning, everyone, and welcome to the JKMRC Friday Morning Seminar Series. On behalf of the University of Queensland and Sustainable Minerals Institute, I would like to acknowledge the traditional owners and the custodians of the lands on which we meet today. We pay our respect to their ancestors and their descendants who continue cultural and spiritual connections with country, and we recognize their valuable contributions to Australian and global society. And for this seminar, it's my pleasure to welcome Dr. Eric Ansah, O Ansah, better. Eric works as a postdoc research fellow at MIWATCH. He's currently working in MIWATCH group to apply his expertise in geochemistry and hydrometallurgy for metal extraction from mine waste. He has worked in metallurgical and geochemical research, plant operations, translation of research to industrial startup, and technology development. Some of his projects and studies involved copper, gold, silver, cobalt, uranium, and rare earth elements. Today, he will present a seminar titled Low Energy Efficient Copper Extraction. So let's give a warm welcome to Eric. Thanks.
Good morning, everyone. Thank you very much for coming, and I'm quite grateful to be the last speaker of the year, I think. So I'm going to talk about low energy efficient copper extraction today, and we'll start this way. So this is a low-grade ore material that I received during the early hours of my PhD work at the University of Melbourne. And I did 4 months of characterization, so doing SEM, EPMA, thing sectioning and the likes, XRD, XRF. Unfortunately, after 4 months of hard work, there was very negligible copper, loads amount of galena and sphalerite. So that sort of motivated us to develop combining geochem and hydromet new ways to extract copper, but then considering energy consumption for grinding as well as water use. So our motivation stems from, as we all know, the fact that we are transitioning from a high carbon economy to a low carbon economy. And copper is like the lifeblood of the electrification process. So you need copper for almost everything. You need it at data centers for copper wires. You need it for EVs, which we all love to drive one day in a Tesla. I love to drive a Tesla one day. We need it for wind turbines, solar panels, and the likes. But then there's a challenge where there's not much copper. So we need to produce more copper to meet the growing energy demand. So BHP this year predicted that the global copper demand would grow by 70%, over 50 million tons per annum. So meaning from now till 2050, we need by 2 million tons. So 2% every year increment in that direction. So to reiterate, we're moving or transitioning from a low carbon economy, a high carbon economy to a low carbon economy. We need much more copper. But then currently, there are mostly low-grade copper ores, which are copper sulfides, chalcopyrite being the most abundant, mainly because we've sort of used most of our copper oxides, which are easier to process. So we now have abundant hypogenes, copper sulfides lying around. These are low-grade ores, which are difficult to process. They consume more water. They produce more waste. Also, they are mostly located at places where there's water stress. So you talk of Atacama Desert of Chile and then places in Australia. It's predicted that beyond 2030, there will be water shortage. So the key question we're trying to answer here is, how do we produce copper to meet the growing energy demand whilst preserving water? So to take you back to why we need more copper and the fact that there will be copper deficits, almost 7% according to BHP annual report in 2020, due to grade decline and resource depletion. Because we have low-grade ores, they need more water to produce more waste, and they need more energy to process. A solution, according to the International Energy Agency, is heap leaching. So heap leaching, because if you look at the graph on your right, and you consider your estimated energy intensity against your copper grade. So if you take for low grade or 0.7% copper head grade, you're using almost 20 gigajoules per milliton of copper, as against in a similar vein for 0.8%, and you're finally crashing it to get concentrate, floating it, and probably leaching it thereafter. you need almost double the amount of energy in that with respect. So heap leaching, it's really good in terms of energy usage and in terms of we getting copper to meet the growing energy demand. So what then at all is heap leaching? So basically, if you're not a mining person and you're listening, so you have a pile of rocks ranging from very fine material to coarse material, boulders, onto a pad, and then you connect piping systems, load up more piles, and then at the top you have sprinklers, which is trickling down lixiviant. In the case of copper, often is acidic lixiviant from the top to the bottom. At the bottom, sometimes they have air sparges at the bottom to help oxidation. And then what then happens is that your fluid trickles down from the top to the bottom, contacts your mineral of interest, in this case, your copper minerals. It mobilizes the copper into solution, which is collected into a tank at the bottom. And then you get your copper for further refining and processing. It's a really relatively so-called, if you look at the picture or the video, simple process, but then it's quite complicated in that you are involved in kinetics chemically, and then you're considering flow and transport, which complicates the whole issue. Due to that, often heap leaching reports low recoveries for copper. So one reason, which is well known in the industry from a geochemical point of view as well as a hydrometallurgical point of view, is this. So if you take a grain of ore material, in this case, you're looking at a pore-free copper material. So at the top picture or image, you have your bornite, which is your purple brown colored mineral, and then your chalcopyrite, which is your bright yellow mineral. And these are buried within feldspathictic veins or quartz veins. For some time, after leaching for say 30 days, in our case, you have transformation of phases and development of new phases. So what we are seeing is, first, a darker material around the rims of your copper sulfide mineral, identified as jarosite. And then you have a bluish mineral, which wasn't there initially, but then it's forming. So there's a secondary copper sulfide mineral, cobalite. And then you have where the chalcopyrite was initially, it's being transformed more to a deep brown material, bornite in this case. So realistically, the formation of these phases results in less copper dissolution. So if we translate what's happening in these two images onto a graph of changing copper concentration per time, what we observe is for the fresh surface, initially, there is high dissolution. So you get much more copper in solution. But then the very minute these phases starts to form, there's nucleation of the phases, there's precipitation, and then that causes a decline in the amount of copper that you are reporting to solution. So that's the whole cause, or one reason that the industry has identified leading to low copper recovery. It's called passivation in hydromet literature. From a geochemical point of view, it's sometimes called surface armoring. So to elaborate further what the science behind this is, it's very simple. Assuming you take grains of salt or sugar, you put them into solution. If it's salt, you have NaCl, it dissolves in water, your Na, your Cl. If there are some other things in the water, obviously, which there is, it then combines with your sodium or your chloride, reaches saturation, and then something else forms. So in this case, literally, we're saying you have your mineral AB in aqueous solution, it dissolves. There's release of A and B, combines with C in the system to form a new mineral AC. So this new mineral sort of occupies portions of the initial reactive surface area of your underlying primary mineral. And if that happens, then it seizes or sort of inhibits how much A and B you can get into solution. And that is a concern. So in the case of chalcopyrite, what you're having is in the presence of oxygen and some ferric, which are oxidants, and then there's water, you'd have CuFeS2, which is the formula for chalcopyrite, breaking down to get your Cu, F, and S, which is sulfur, sometimes oxidized into sulfates. But then due to the presence of gangue minerals, like feldspars and muscovite and biotite and the clay minerals, they release things like potassium, which then combines with your iron and your sulfate coming from the chalcopyrite to then form a new phase called jarosite. And this jarosite, as you've seen here, sort of occupies portion of this initial mineral surface area and inhibits how much copper we can get into solution. We think, and from our research, realize there could be many instances of this passivation mechanism or surface Amore mechanism. Take, for instance, you're making sandwich, you have bread, you put batter on it. You can choose to cover the whole surface of the bread. You can choose to cover portions of it. And all these have several consequences. In this case, how much copper you can get into solution. So if you start from one where the fresh surface, there's more copper, you could be forming things which are soluble, if you're lucky enough. If it's soluble, it means it comes back and then you could get your copper. But then if it's thick and it's dense, then you don't actually get much copper in solution. If it's porous, we think that you could still get your fluid permeating through the pores and contacting the primary surface copper, So we can actually translate what's happening here in these images onto a simple curve of this nature, where we'll try to understand if it's porous, if it's non-porous, if the precipitate is soluble, it's non-soluble, what's the effect on the amount of copper that we can get in solution. So if you plot a graph of percent element dissolved of copper per time, initially fresh surface, you have much more higher rate of copper mobilization. With time, if you form insoluble non-porous thick layers, which often sort of cover the reactive surface area, and inside a heap, it clogs the pores, you then have a decline in your copper. But then if you're lucky enough to form things which are soluble and porous, then you could still have somehow linear rates. But then if it continues that you have more insoluble, non-porous thick layers forming, there's sort of a decline in the copper amount and your heap leaching system becomes less efficient. You then get more copper that you need for your energy transition. So the signs of copper leaching, it's well known. So it's been a century of work done, and there's been so many nice ideas as to what works and what doesn't work. Some of them well applied in industry. So past ideas for inhibiting passivation of surface Amore, one is that, so I'm gonna make mention of a few of them here because there's a lot. You could continuously during the leaching process or the dissolution process, tip in more acid. So quite often sulfuric acid. But then what that means is the more sulfuric acid you use, you need to buy it with money. So your operation cost then goes high. In some instances, this research coming from the guys in UBC where they think there could be galvanic interaction if you have pyrite in your system, which sort of helps chalcopyrite itself, patented it as Galvanox process. There's the use of thermophilic microbes. So if you have microbes which can withstand heat, geochemically, if you have high temperatures, you could get high kinetics for your copper. Dissolution. There's also the use of catalysts like silver and vanadium, where their presence could then help ensure that you get much more copper in solution. So we are doing something different, and that's what I did in my PhD. So two key hypotheses. One is that from all the images I've showed you in terms of Amore and passivation, we think rather than looking at it from a physical coating perspective, you can look at it from a chemical perspective where there's intermineral competition for specific ions. So in this case, you have chalcopyrite, which has CuFeS2. It has Fe in it. You're forming jarosite, which also has Fe in there. So it means to form more jarosite, you need Fe. If you have Fe in your system in the form of ferric, which is an oxidant and needed to get your copper, then it will be consumed by your jarosite. So you don't get more ferric in solution to get your copper mobilized. More so, we think, so from the images I showed you and from the analogy I made for your sandwich, if you have something that's porous, so assuming you put patchy porous layers on your sandwich and you pour water, you could get some water contacting your bread and soaking it up. But then if it's thick, then it means the water stays on top of your margarine or your batter or anything. So the same idea applies here. If we form something that is porous, then we could still get our lixiviants or our fluid permeating through it to contact to leach our copper for us. The whole overall goal is then to mobilize copper use brine, highly saline brine, waste brine material, rather than fresh water, so that we don't consume much more water. So I'll present two case studies. So one is where we did a simple batch leaching, and the other we use columns. So our main goal is to know what is forming, where is it forming, what then is this effect on the surface area of your chalcopyrite and the amount of copper you can get. So the material we're using here is a low-grade porphyry copper ore from New South Wales in Australia. It has about 1% chalcopyrite, almost 96% silicate minerals, feldspar, quartz, and the likes. So in this image, you find your bornite side by side, a chalcopyrite with a chlorite mineral. And then these are all gang material, feldspars, and albites. In the hand material that we took, you have your chalcopyrite buried within quartz vein, and then your feldspar surrounding it as well. We packed these material, almost 1 mm particle size, into a column, and then we took EPMA and mineralogical map of it. So you can see your copper sulfides, bright yellow faces, and then most of it being your gang minerals, your feldspars, your albite, and your quartz. Our focus here is target low-grade materials which are abundant, use brine water, do less temperature conditions for copper leaching. So first, that's simple experimental setup. Conditions we're using is something called protonated brine, comparing it to sodium chloride-rich brine, which is known in industry. In Chile, they use it a lot. Calcium-rich brine is actually a patented technology, and acid only, which is obviously well known. We're doing low temperature conditions, 25 to 45 degrees, pH 1 to 2. And we're using granulates, which are coarser rather than fine materials, because we want low energy systems. So 0.25 to 1 mm. And then we're using something called wafers. So these wafers are sort of rectangular slabs that we cut, which I'll show you very soon. The idea was then to have a surface which could tell us where the passivates are forming and how it's influencing the system. And then post-experimentally, we're doing all these. So first sectioning, reflective microscopy from a geochemical point of view to see what's happening mineralogical-wise, EPMA and ICP-OES. So to the metallurgy. So what we do is that we first take the hand sample, and then I cut a slab rectangular material like this from it. And then I use a microscope, ZSI microscope with TrackWest. So TrackWest is software developed at the University of Melbourne. With that TrackWest software with the microscope, is able to give us a larger surface area of the slab. And so it takes smaller images, we mosaic all of them together, we get a very big piece. And then I'm able to pick specific points of interest. So to me, my regions of interest were these veins where the sulfides are located. And I sometimes also pick around it where the gangs are. So that I'll do chemistry analysis to see what happens to the system before and after. So using the same points. So the good thing with this TrackWest was that you get your points with a ZS microscope, and then you're able to translate the same points to the EPMA machine, and you drive to the same areas of interest that we picked so that you don't do a mismatch. So we took the same surface, took the points, gave it to the EPMA, and then from the points we selected, we did chemical analysis, spot analysis to see the mineralogy and the chemistry. Some results. So one, leaching in acid only. So if you leach in acid only, what we observe is that from the reflective microscope, your fresh surface, bright yellow chalcopyrite with your alkaline feldspars. After 30 days of leaching, what we observe is apparently your chalcopyrite is not leaching. It's rather transforming into several phases. So you have it transform to bornite, cobalite, the transition phase, and apparently nothing happening to your feldspars, or maybe something, but that we don't see in these images. And we also did a sort of a 3D representation to see what's happening. So from the 3D point of view, where the blue areas are, we think there is dissolution happening. And then where the red areas are, we think there's precipitation happening. Using the same points of interest, giving it to the EPMA to understand the chemistry, we realized there's actually negligible copper, as we saw in this image. There's apparently no copper dissolved. It's rather transforming, but it's not dissolving. So this is what we had. for leaching in only acid. If we put in ferric, so at low pH conditions, what we observe is that if you have bonates lying side by side chalcopyrite in your fresh surface, after 30 days of dissolution, you have copper mobilized from your bonates. It leaves behind something like a ferric sulfate phase. And then your chalcopyrite is bright yellow, sort of transforms to more bonates rather than dissolving. So in this case, there is dissolution of copper from bonates, but there's apparently no copper dissolution from where your chalcopyrite is. And this was proven by the EPMA as well. So for the points where we did the analysis, the areas where there's bonite, we see a decline in copper, meaning it's being dissolved. But then where there's chalcopyrite, we don't see anything. There's actually a negligible change in the copper before and after. In the solution we proposed, which is the Liseviant we proposed, that was a different case. So at the end of the leaching, we observed so many phases forming, and the texture is not really nice as we saw before. But the good news here is that we're getting copper from both chalcopyrite and bonite. So you have more ferric oxides forming. These are metastable, mean they are metastable. They can form and easily go back again into solution. You have ferric sulfate phase forming as well. And then from the EPMA, we see that there is decline in copper for both chalcopyrite and bonite, unlike the previous two cases which I've shown you. So we then went ahead to optimize what we saw. So we did further leaching tests just to see what's happening in the system. So under all conditions, when I say all conditions, what I mean by is varying temperature, varying pH, and the likes, we can tell there's much more copper for the protonated brine Liseviant compared to if you use sodium chloride rich brine or ferric chloride or acid. And that was really interesting. So one reason why we think that's happening is from these activity diagrams. So plotting the EH and pH of the system, we realize that, so if you look at the fresh water, you have phase like ferric sulfate forming, and that's pronounced as well in that, and in that. But here you realize that the region of that ferric sulfate is sort of declined. So you have things like aluminite and aluminum sulfate forming, which sort of declines the amount of ferric sulfates. But the formation of ferric sulfate is not good because you need ferric, which is an oxidant, to get your copper. But then if you're forming more ferric sulfate, it means your ferric is going into precipitation rather than staying in solution to get your copper for you. More so, if you form more jarosides, that's also not good because then your ferric is going into form jaroside rather than getting your copper out for you. So we think that you could form things like aluminum sulfates, which is not consuming your ferric and is helping your ferric stay in solution to get your copper. Theoretically, we wanted to understand, okay, if we form precipitate and we're able to predict its thickness and we relate it to the diffusion rate of, say, your ferric in solution, what then is the effect comparing your sodium chloride and your protonated brine? So in the case of sodium chloride rich, we predicted, say, the thickness of jarosite to be around 35 micron. And with that, you have a decline in your Fe diffusion coefficient with time. Whereas in the protonated brine, even though we're getting the thickness around 25, what is forming is sort of soluble and is porous. So you could still get your Fe diffusion coefficient very high, 1.6 E minus 2 meters squared per second. So the conclusion here was that the persistence of more soluble porous precipitates could sort of help copper mobilization. The next case scenario is column leaching. So column leaching because it's very representative of a heap system where you're flowing and you're kinetically leaching your copper. So the similar objectives, what is forming in terms of its composition mineralogically and chemically, how is it forming, what is its influence on the surface area and the copper amount that you can get. So we use very tiny columns because we wanted to micro-CT it before and after. The micro-CT machine is small, we can put a very large column in it. So very small column size, pack some quartz from Bunnings at the bottom and at the top, and then put your copper material there. This was pure quartz. So we tested this XRD mineralogy and yeah, it was pure quartz. So particle size, we did fine and coarse. When I say fine, in my case, it's not microns, no. It's still millimeter size. And then we tested it for leaching media. And then we did 2 instances of flow rate. So we wanted to see what's the influence of high flow rate and low flow rate on your copper amount. Then afterwards, we have these post-experimental analysis. So section it, get to see mineralogically what's happening under a microscope, EPMA, and then micro CT the whole column before and after to see what's happening. So in sectioning, after the experiment, I'll normally flow first water through it. So you flow water through it to get the excess residues out. And then I put acetone and epoxy 1:2 ratio, then flow it through it as well so that you get epoxy in the material. And then put in a stress acetone, which is a really good material equipment. So you fix it there and then you're able to cut automatically without you cutting with a saw and breaking it apart, the integrity. So you take that, you section, you get this. Then we'll put fusidial marks here so that we know that we're going from the bottom to the top on the microscope. So this is what we get. So with the ZMZS microscope, with the trackware software, you're able to get a large surface area of this section, and then you can then pick points of interest. So in picking points of interest, in one of the cases for the fines is what we had. So with larger surface area, we flow in from this direction, from the left to the right. We observe clearly ferric oxide balls. These were in there before we started the experiment. And then if we pick specific regions of interest, so you could see ferric sulfide ring and then chalcopyrite. And then if you zoom in also on other sides, you have cobalite, where your chalcopyrite is actually transforming to cobalite. You have more ferric oxide balls. And then in some cases, we have silica gel formation. So silica gel, because obviously, when you contact acid with your feldspars and your silicates, in some cases they dissolve, in some cases they don't. In some cases they dissolve and leave behind silica residues or silica gels, and that's what you have. And these, if they are numerous, they sort of clog your pores, and it's not good. So, sorry. So from that same surface, we then pick those points, send it to the EPMA, and then that can give us a BS image and can also give us elemental maps, and we can combine the elemental maps and get a mineralogical map. So I didn't have money to do ChemScan or MLA, but then the good news is softwares exist. So there's a software called XMap Tools. You can get chemical maps from EPMA, put into it, use random forest or machine learning, and then you can segment to get mineral maps. And that saved my life from doing MLA or ChemScan. So different instances. So what I want to tell you here is that if you look at these 3 figures, you can see that you could have an instance where your precipitates are sort of going at the entry point of the column rather than all through it. In other case, you could form the precipitates along preferential flow pathways all throughout the column. In some instances, you could have it just at where the copper sulfides are, not throughout. And whether you form homogeneously throughout the column or heterogeneously, it has different consequences on how much copper you can get, how quick the flow can be, and what's clogging the pore space. So this is what we did. We observed for the protonate brine, we observed jarosite formation, mainly at the entry points, and at the exit, not much. But then for the fine material in sodium chloride-rich brine, you have it preferentially forming along the flow pathways and all the way throughout the column. You also can see some ferric oxide balls which are forming. For the acid, we don't see much. What we see is just tiny bits of jarosite forming at where your copper sulfides are. So from here, we then took the same section columns with the same fusidial marks, mounted inside a GE nanotome micro CT machine so we could drive to the same points. But the good news with micro CT is it scans the whole thing, and then from there we can go and do analysis. So the section column that we had with the fusidial marks, we can get something like this, which cuts across everything here, and we can as well get a 3D of it. So here, the brighter faces that you're seeing are your chalcopyrite and your bonates. The bad news here is that we can't really tell which is bonite, which is chalcopyrite, but they are all sulfides. Also, you have your gang material, which is the gray material. The bad news is we can't tell a biotite from a feldspar. or muscovite, but we can then segment everything altogether. So we did segmentation in a software called Dragonfly. So what we wanted to see here was, as we saw in the EPMA, is it forming all throughout, or is it forming more abundantly at the entry points? So to make my life easy, after trying with current machine learning and failing, I did manual segmentation. So segmented the faces into my sulfides. I didn't bother separating bonite from chalcopyrite because that was tedious. I didn't also bother so much separating clay minerals from silicates. That was also very tedious. So I just did these three. Separate my precipitate from my sulfide and then from the silicates. So for the fine materials at low flow rates, you have virtually the precipitate all throughout the column. For your coarse materials, you have it just at the entry point and some at the middle, but very little at the exit. Another thing is, so before I sectioned, I took the whole columns and then microseated it so that I could predict porosity, because the goal here is to see what is forming and how is it clogging the pores and how is it preventing copper dissolution. So if you microseat your fines, you get something like that for your coarse materials. And then afterwards, I then segmented it into two phases, so pores and solids. So you have your fines there, you have your coarse materials. The blue region is your pores. And with that, you can get something called a pore network. So for a pore network, you're looking at simple analogy. You have two balls and a stick connecting the balls. So your balls are your pores. The stick is the connectivity between the pores. This is important because there could be pores, but there will be no connectivity. And there could be connectivity, but there will be no pores. So we want to understand what's the influence quantitatively of this precipitate or jarosite that's forming on the pores and the connectivity throughout the column or the heap. So for the fines, you see there are virtually very small pores, whereas for the coarse material, you have very big pores. Quantitatively, if you form precipitates, this is what we observe from that segmentation analysis. So if you take your fines in sodium chloride rich brine, we realize that there is less pore decline due to dissolution and precipitation, whereas the coarse materials results in higher amount of decline. So about 9% for your core material, still around porosity of about 0.5, 0.55, declines to 0.45, 0.3 in some instances, whereas you don't see much here for the fines. For the connectivity, which is the stick between the two pores, so we realized that decline in the throat radius was virtually due to precipitation, and that affects the overall connectivity of your pore system in a heap. So for the fines, we have smaller throat radius, and in all cases, when the precipitate form, it causes a decline. For the coarse materials, we have some finer throats and some larger throats. The larger throats sort of decline, but then the finer throats increases, strangely. What does this mean for copper extraction? I guess that's where we're driving at. So if you plot a graph of copper extraction per time, for coarse materials in that protonated brine at high flow rates, we get high recovery for copper, nearly 90% or more. I should say that in all instances, for both high flow rate and low flow rate in the protonated brine, for coarse material, we're getting much more copper compared to in sodium chloride rich brine and in acid. You can only get high copper for sodium chloride rich brine in the experiment we ran if you increase the surface area. That is, if you grind finer, then you can virtually get much more. But then for acid, no matter what you do, you still get less copper. To conclude, so in summary, what have we done? So one, we've shown that it's good to treat passivation as intermineral competition for iron, so we get much more copper. And in comparing protonated brine, so the protonated brine Lisivian that we came up with outperforms sodium chloride rich brine, which is used in industry, ferric chloride, as well as acid. And This protonated brine is cheap and is widely accessible in the water industry. In the agric industry, they use it a lot, as well as in some pharmaceutical sectors. What we need to do, which is the next steps, is to use this Liseviant and what we know about copper heap leaching and try it on different ore materials. So far, we've used porphyry copper ores, and we think it works per the results we have. And not long before I joined SMI, we tried it on IOGC sample. So this IOGC sample, the focus was not only copper, it was to track copper, cobalt, gold, REE, and it gave us good results as well. So we get much more lanthanums and ceriums in solution. We got high copper, we got gold as well, compared to using acid and compared to using ferric. So I guess the next step is just to see if we could try it on different ore materials from different parts of the world to see how best it works and how best we can generalize the system, and then do a field trial, upscale it, and see if we get much more copper using less energy, not grinding finer, and using saline brines. So I'm quite grateful for the opportunity. Medase, so I'm from Ghana, so Medase means thank you. Quite grateful for the opportunity to present today. I want to thank my supervisors and members of the Peter Cook Center. That's where I did my PhD at the University of Melbourne. And I thank the SMI UQ MIWATCH group for the opportunity to sort of continue this research, apply more to mine waste, to low-grade ores, get copper and other metals without grinding finer, without using more fresh water. And that way we can make the world a better place, more greener in a less carbon economy. Thank you.
All right, thank you very much, Eric. Very interesting presentation, very well presented. I love the models and figures quite well. I'm going to start with a question. If you are to use those experiments to upscaling, as you said, what challenge would you think you'd face when you start to upscaling and with external factors?
So I think a lot. So the batch system is very much ideal, and it's often the first step in most leaching studies. But then in the case of heap leaching, it's really not realistic, because then you're flowing something, there's preferential flow. So assuming there's rainfall, you have a pile of rocks, the rainfall could choose to pass through certain pathways depending on porosity. And who knows, maybe where it didn't pass, your copper could be sitting there and you couldn't even contact it to get your copper into solution. Most of the columns we use are very small and tiny, because then that was a proof of concept. To use bigger columns, more materials, we can, even for the small columns, we see preferential flow pathway. For the bigger columns, we think there'll be more preferential flow pathways. So that'll be a huge challenge. To do it on the field is a different ballgame altogether, which is not ideal in a scientific environment. And yeah, predictably, we think there'll be a lot of challenges from engineering point of view. I think a few things we're trying to consider is, how do we keep the moisture saturation or the amount of water in the heap constant? Because then we think if you have more water in the system, it means you get more fluid rock contact, and then your dissolution will be better. But then if you're flowing it, the moisture content or the solid liquid ratio is sort of variable. So you can't really predict what's going to happen in the system. So these are things we're thinking around engineering wise, how best to do it so that the geochemistry and the geology makes sense for us to get more copper. Yeah.
Now, how weather can influence this kind of experiments?
I didn't talk about that because I'm human. So that's unpredictable, because yeah, in most heap operations, especially say in Australia, where you have dry seasons and then some rainfall. So in very high intense dry seasons, there's high evaporation. That's a challenge. Whereas when it starts to rain a lot, you get your heap being soggy. That's also a challenge. So for that, I don't know. Yeah.
Thanks.
Cheers.
Apologies if I missed it early on, Eric, but what acid were you using in these tests, and did you use different types of acid, and would you expect different results from using different types of acid, say hydrochloric, sulfuric, nitric?
Yes, so we did try both sulfuric acid and hydrochloric acid. So in the batch ones that I showed you, averagely was the hydrochloric acid that gave about 5%. The sulfur gave just 3%. But then in that protonated brine, there's no acid, because then we're using high amounts of chloride. It's a weight brine system. If you have high amount of chloride, automatically your acid stays low. So we're not tipping acid into that protonated brine. Yes. Yes. So it got low pH. Yes. So yes, but then we are not putting in extra acid. That's the trick here. Yeah. Because then our goal is to cut down on reagents in terms of acid, cut down on energy in terms of combination and the water usage. Yes.
Thank you, Eric, and congratulations. I think it's a brilliant piece of work. It's so refreshing to see some hydrometallurgy at some of these
Sure.
Friday seminars. My question relates to something that's probably a little bit outside the scope of study, but still important to consider, and that is what happens downstream.
Okay.
You know, you dissolve the copper. Yes, you can do that, and then you have to recover the copper. Traditionally, that's done through electrowinning mostly. Electrowinning is a very sensitive process to other strange species in solution. Can't remember the electrochemical series, but you know, now you're starting to introduce certain things in there. Have you thought about what will happen? How would you get the copper out? Also remembering that barren solution after extraction or after precipitation or electrowinning goes back normally. So you reuse that same solution through your leach process. And also an interesting one is what happens to the iron? Because you don't really want iron downstream as well. Does your iron, you know, what's the response? Have you got any comments on that?
Sure. So I think about 5 months ago, I was asked a similar question I couldn't answer. But then after thinking about it for a while, maybe today, maybe I could give an idea. So yeah, we've thought about it in terms of, so you leach your copper, you have it more in, say, cupric chloride or cuprous chloride, how to get your copper from that solution, probably doing solvent extraction and afterwards carrying on to something. But then I was speaking to James, and he was thinking about, James Volgan, he was thinking about precipitating the copper out. So if we could precipitate it as copper sulfides or even copper hydroxide, then that means we could get copper in a better form and take it for subsequent processes. The other question as to recycling of the lixiviants, that is something I'm still thinking around the day in and day out. So yes, you do not want your iron back to the downstream process, because then it will compete with the copper when it gets to the other stages. But then, no, I think that's something that we need development with. And probably if we have a good industry partner, they can then help, and we could try out it and see what's the best way forward. Yeah. So, yeah, thanks. Yeah, cheers.
Hi, Eric. Thank you. Just a question around particle size. So, I mean, you've got the coarse and the fine, but obviously there's a range of potential granulometry in there. So I guess two questions. You were showing quite good results with the coarse, with the protonated, which is fantastic. From a point of view of comminution, do you look at that as well in terms of, is it to do with the copper species and the potential liberation size to particle size? How do you decide what the optimal top size, grain size should be when we talk coarse versus medium versus fine? Is that part of your study and results as well?
Thank you, Mark. I think there's something maybe I can do at SMI. So initially it was a proof of concept to try to see if we could get copper from coarse materials. We didn't consider if we have a varying range of particle size, granulates, what's going to be the consequence, or probably what's the optimized size. I think something which probably I'm thinking of doing with one industry partner is to leach for different particle size, and then also leach for a combined particle size to see whether it works or not. And yeah, like you said, you're right to say, so if we crash it, or even if we blast it and we heap it, we definitely have varying particle size, which will affect the liberation. But I guess the point here for the protonated brine is the fact that even though the copper sulfides are occluded or non-liberated, we could still have that lixiviant sort of permeate through to leach our copper for us. So that's something that we were amused by. Yes.
Okay, so we have some online questions. The first one is from Mikhail. He asked, have you had any thoughts about the impact of photonated brines on materials of construction for SX, EW, and the extragent life?
Can you come again? Sorry.
If you want to read it, you can read it on that screen as well.
Okay.
But yeah, I'm not sure exactly what extragent life
This one.
means. But maybe while we're getting that, another question from Tim. He says, fascinating, thanks. Have you done any thermodynamic modeling to predict? So,
No, you do the second question. I'll think about the first one. Yeah.
okay. So Tim asks, have you done any thermodynamic modeling to predict the solubilities, etc., at your specific conditions? If so, was it reliable and useful?
Oh yeah, so I will answer the second one first, and then
Okay.
probably I'll think about the first. So yes, so I think I showed you EHPH diagram, which is a modeling that we did. So often what I do is before the start of experiments, I try to model what to expect in the lab, because then from the lab I came from a geochemical point of view, we want to see before we get there, and because we don't have much resources, that saves us time and money. So we often model it in GWB or FRIXY, which are well known in geochemistry. So use that, model it, plot Pube diagrams, EHPH diagrams, stability diagrams, mineralogy, saturation indices just to see. So after the experiment, we'll take the fluid chemistry and we'll plot similar thermodynamic diagrams as well. So all the diagrams I showed you for the sulfate, I have similar stability diagrams or thermodynamic diagrams for copper and also for chloride and likes, yeah. So, and those were useful. So those told us, say, in terms of copper species, is it free copper? Is it copper chloride? Is it cuprous chloride? Is it copper sulfates? The same for the ion as well. So yeah, that was useful. So for the first question, materials of construction for solar. Oh, okay. So I think I understand what he's trying to say. So
Oh, sorry, he said he had a typo. It's not photonated, it should be protonated.
okay, yes.
Yeah, thanks, Mikhail.
So yes, so I think it's similar to what was asked as well, in terms of what's the influence of the lixiviant on downstream processes, like say solvent extraction or yeah. We've been thinking about it in terms of, so that protonated brine has high halides, so high chloride amount. So it means it could corrode the tanks. And I think the industry now sort of understand halide leaching of copper, and they've been trying to design either titanium covered or steel covered tanks, which will sort of withstand corrosion. So I think when it gets to the engineering, we could borrow ideas from that and use it. Yeah, that's what I'll say.
All right, thanks. Any other questions nowadays? Oh, Quentin have another one.
Thank you. Your tomography work was fascinating as well. Even though you can't really do the chemical analysis on that, at least you can see what's happening. Did you at any stage consider to take snapshots in time? In other words, starting and then after 1 hour, after 5 days, and that sort of thing, to see how the pore structure changes over time as well, to try and get some sense of the kinetics of the process.
I'll say no, unfortunately, because that microcity is always busy. So the time I had was just to scan it before and scan it after. And because I wanted to scan the whole column, it took a longer time. So if you want a better magnification for you to see the mineral, so you could segment. So assuming you want to do that 10 microns, I remember one scanning could take almost 4 hours for us to scan. And because we are considering a very large column size, I think probably if we had done just smaller, tiny portions of the column, then I could have been able to do the time series and do it probably after every hour, every 2 hours. Yeah, but I couldn't do it. But there are groups around the world which have done something similar. In terms of segmentation, I think the next stage of the segmentation work will probably, I think the SMI can probably consider as well as. So in this work, we're trying to see if we could use the EPMA chemistry and then map it onto the micro-CT and use that to segment the micro-CT. And if any of these micro-CT manufacturers or image segmentation softwares could do that, that'll be like a breakthrough, because then it's really challenging. So if we can then take that chemistry from the EPMA, do a first mapping, match it onto it and segment, that'll be nice, yeah. But for now, not able to, and machine learning is not really helpful as well, yeah. Thanks.
I have another question. So if you had like infinite fund some ways, and you could use any analytical techniques to do a better characterization or whatever, which instrument would you use to better characterize your steps through the leaching process?
Okay, sure. So I think from the review of the work and yeah, listening to or speaking to a number of people, I realized I could do more. So I only limited my work to EPMA, microscope, micro-CT. That's all I had. And then a lot of fluid chemistry. So I think I can do nanosims, I can do MLA, ChemScan, I can do proper segmentation, possibly liaising with someone who has much more knowledge in segmenting micro-CTs than myself. Probably that could be an industry partner coming on board, maybe from ZAIS or from FEI. And they could use, if I have a lot of money, they could then scan it better at very low resolutions, give me very nice images, and then help the segmentation exercise. With the Dragonfly, I was trying to get these guys in Montreal who manufacture the software to help me do it, but then they were busy. And I guess, yeah, if I have money, that's something I would want to do, yeah.
Yeah, you know, like we have a micro-CT here, and also some people that work in imaging processing.
Sure.
Gordon is working, so there's always some
Yeah,
talk could go around.
That'd be nice too, yeah, to partner and do that.
Since we got plenty of time still, I was wondering if you could just walk us through the 3D images that you had on some of your slides, where you had a collection of images of different mineral maps. I think from memory, the scale was degrees of dissolution on there. I was just wondering if, so if you go back further, in the lower right-hand corner, you had a little 3D image
Okay.
there.
Yep. Okay. Yeah.
Yeah, I was wondering if you could just walk us through
Okay.
how you generated that image and what it's telling us.
So that was done by another software. Forgive me, I've forgotten the name, but I can find it for you afterwards. So what we did was that, so in that software, if you give it before and after images of, say, SM or BSC image from EPMA, and then you choose points of interest, it could sort of correlate the two images and then tells you the depth of height, because then you want to do an analysis to see what's happening before and after with the changes happening and also around it. And then, yes, so it could tell you the quantity of change because we're doing per time. So before and after, quantity of change. And then, so I give it these two images and the scale has to be almost the same or almost near there. And then it would then do the quantity of change calculation and then give you a 3D stereoscope. So 3D height, sort of an height image of it to tell you what's changing, what's forming. Yeah, so that's how come we get something of this sort. Yeah.
Oh, cool. Thank you.
All right, I think that's a lot of questions for Eric. So I would like you all to thank Eric for his presentation today. So today's the last presentation from this year for the JKMRC Friday Morning Seminar Series. Hope you all enjoy this year's presentation, and yeah, hope to see you all next year, early next year. Thank you.